of the method of reduction of order. Okay, so now we continue this example. By inspection, we find one solution, which is polynomial of 1, right? Here or not? And so we let y equal to y2, and which is u y1. Okay, so we want to find second solution, which is linearly independent of the first solution. So we try something that y2 is equal to y1 plus another function, and the u should not be a constant. Otherwise, if u is a constant, then y1 and y2 are linearly dependent, so it's useless. Okay, so we have to bear in mind that we should find a function here. Okay. Now we know y1 is equal to x, so we know this is u times x. Okay, so we try to find y2, which is equal to a function u times x. Now we go back to our, because this function should satisfy our original ODE. So now, so this implies that y2 prime equal to u prime x plus u. Okay? So we use the product rule of derivative. So this is this one, and y2 double prime is equal to 1 u double prime x plus 2u prime. Okay, so by taking the derivative again, you find this one. Now, you plug these two formulas back to our ODE. We have x squared minus x, y double prime, which is u prime x, plus 2u prime. Okay, and minus x, y prime is u prime x plus u, and y here, y is ux, which is 0. Okay. So we will this implies and x u double prime, okay, plus so we have 2 x prime minus 2x minus x squared u prime plus minus xu plus ux is 0. Okay, and we cancel them. Okay, so we have x squared minus x u prime plus here, so we have x minus 2 u prime is 0. Okay, and finally u prime plus x minus 2 u prime is 0. It is apparent to be the second order ODE, right? But by letting u equal to U prime. So we let the capital U as the first derivative of derivative. We have this is square minus x equal. Now we have end up with first order already, and we can solve it by a separable variable. So we have equal to minus here. So we have separable, and by partial fraction, remember, right? You know the partial fraction technique in integration. So this is equal to 1 over this one to x. Okay. All right, so we have okay, and this is equal to so U is equal to x squared. Right. So we find the solution. Actually, there are many other choices, but for example, you can add a constant, something like that. But we just want one solution, right? So we are satisfied with just one solution. Okay, so this is 1 over x squared. Okay. So now we obtain a U, but U is equal to literal U prime. So U is the integration of capital U, and this is equal to this one. Of course, you can put a constant again. You just need to find one solution. Okay, one solution is enough. So okay, so now so this is implies y to x. Which is equal to, okay, right? So our second solution is ux times y1x, and this is equal to x, the logarithm of x plus 1. And of course, because u of x is not a constant, so y2 and y1 are linearly independent. we find a general solution for this ODE. Any questions? Okay, please let me know if you have any questions. So the method of reduction of order works for this example. And in the following, I will show this method is valid in general. Okay? So I will derive it. Okay. Actually, it's a proof. But I hope you understand the idea from this example. The point is that we end up with such a special type of second order ODE. Okay? We don't have a U, right? In this case, the Q of X coefficient is equal to 0. So that's why we can let the capital U as the prime. So turn this second order ODE into a first order ODE. Okay, and then the following derivation is the standard one. Okay, so the key idea is that we must have such a special type of second order ODE. All right, so in general, okay, so in general, consider a homogeneous second order linear ODE in standard form. So it's very important to write the ODE in standard form. Namely, the coefficient of y of prime is 1. Okay, this is the standard form. Now we assume that the solution y1x is not. Okay, so we assume we already know the solution y1. Okay, is not. So we want to find the second solution y1. Okay, so we want to find y2, which is equal to u times y1, and try to find the function u. So now y2 prime is equal to u prime y1 plus u y1 prime. Okay, because y2 is the product of u and y1. So y2 prime is equal to u prime times y1 plus u times y1 prime. And the y2 prime is equal to u prime y1 plus 2u prime y1 prime plus u y2 prime y1 prime. Okay? It's just a standard, right? You like that. And then you do the substitution into this is standard form. So you have u prime y1 plus 2u prime y1 prime plus u y1 prime. So this is the first term corresponding to the prime plus p u prime y1 u y1 prime plus q u y1. Okay. Now you combine terms corresponding to u. Okay. So you have u y1 u prime. So this is the only term related to the second derivative of u. This is the only term. For the first derivative of u, you have u prime. So this one is about second derivative. For the first derivative, you have this term and this term. Okay? So you have 2 times y1 prime. This is p y1 plus. Okay? Plus about the u. So you have u here, and u here. So you have y1 prime plus p y1 prime plus q y1 times u equals 0. Okay? Now, but we know y1 is a solution of this ODE. y1 is the solution of this one. So this term goes to 0. Cancel. You can say magically, right? That is the truth. And so now you have y1 u prime plus 2y1 prime 1 plus p y1. Okay. By letting w equal to u prime. Okay. We have u prime. So you divide it. You have p plus so you divide by y1. So you normalize the coefficients of the prime. You can type this one. Okay. Remember, this one a function of x only, right? Because y1, y1 prime are functions of x. So they are all functions of x. So you can you can apply the method of separating variable. So you have u minus p plus 1 Okay. So you have the logarithm of x value of u equal to minus x and minus 2 and this is the logarithm of 1 x. Okay. Right, and so u prime is equal to u, which is equal to logarithm. So this 1 over y1 square. Okay, exponential minus. Okay. So you see that in general this is positive, right? Because exponential function always positive and square always positive. Okay, of course we have to avoid that the denominator can be 0, okay, by select a proper open interval. But nevertheless, this is always positive. So u becomes 2. Okay, and so this is equal to okay. Right, so u is not a constant in any open interval. Okay, so we get our u function. X and y to x, which is equal to 1x and ux are linearly independent solution such that so this complete all proof of the validity of the method of reduction of order. Any questions? the only price you should pay for using the method of reduction of order is to find a solution by inspection. Okay, by your experience actually. So the following two sections is about special cases of homogeneous second order linear ODEs. The first one is with constant coefficients. Okay, so we consider y prime plus a y prime plus b1 equals 0, where a, b are constants. Okay, very simple homogeneous second order linear ODEs because the two coefficients are constant functions. Okay, special cases. All right. So anyway, if we want to use the method of reduction of order, you have to find a solution. Okay? So somehow you have to guess some sort of solution. So recall, maybe we can learn from our previous experience. Recall a homogeneous first order. Homo means homogeneous because try to set my tongue. Linear y prime plus y a. Right? This is very simple, right? And immediately. Okay, the solution is an exponential function. Very easy, right? You just do the, you can use the separation variable, right? So to find the solution, so actually it's an exponential function. Okay, so we try. So now it suggests us to try the solution for second order homo linear ODE with form y of x equal to lambda x. Okay? So we try exponential function. Try exponential function. Okay, so when we try exponential function, we find that it is equal to lambda, and the y prime is equal to lambda squared. Okay, so this implies that I'll have lambda squared b lambda x plus a lambda x plus b. Right? This is our ODE. Okay, so if this is the solution, y of x is the exponential function is the solution, then this solution should satisfy the ODE. Okay? Now, all the terms has a factor which is equal to e to the lambda x. So we can cancel them because we never 0. So you have okay. So the lambda should satisfy this equation. So we conclude that y of x is a solution of the ODE. Okay? So if and only if, okay, lambda satisfies the second order equation, which polynomial, I'm sorry, the following polynomial equation that we could choose, which is called the characteristic equation. Over auxiliary equation. Okay. Right? So this is the economic condition. Of course, our target, our goal is to find a general solution for this ODE. Namely, we have to find two linearly independent solutions for this ODE. Yeah. But at first, we try, right? We try this exponential function and we find a very good result. That the exponential function is a solution. Okay? If and only if the lambda satisfies this quadratic equation. Okay. All right. Solving the quadratic equation, we have, okay, in general two solutions. And then lambda 2 equal to 1/2 minus a minus square root of a squared minus 4b. Okay. We know a squared minus 4b is called the discriminant, right? And that's fine. So we have 2. So now we have 3 cases to consider. That's fine. Right. If lambda 1 and lambda 2 are distinct real means that a squared minus 4b is positive, right? When this is positive, then number 1 and number 2 are real and distinct. Okay? In this case, then y1x, y2x are to linearly independent solutions of the ODE. And y of x equals C1 plus C2. Is a general solution. So this is an easy case, right? So we indeed find two linearly dependent solutions. Any questions about the first one? Okay, now we go to case 2. Number 1, number 2 is equal to minus 1/2 A when A squared is equal to 4B. Now we have okay, so y1x is a solution. So we find only one solution. But we have the method of reduction of order, right? Once we find one, we can find the other one, right? We just learn the technique. So now we are able to the second linear we already learned this technique. So we try to find UX. Okay, so now so we have U okay. Right, so we know that we have up to this one, and since okay, y1, our first solution to this one. So we have y1 prime is equal to this implies that y1 prime plus a y1, okay, 2y1 prime minus a, which is equal to 0. So this is 0. So this is implies that you have a prime y1 is 0. And the only solution is that C1x plus C2. But there are many solutions, but so we just find x is enough. Okay? Just find a very simple solution. Okay, so we just select u equal to x. So y2x is equal to u, y1 x. So this is E. Okay. And that's okay, so we solve the second case. Alright, so the second case, the general solution is C1 plus C2x. Okay. So it's a linear function times exponential function. Okay, so you can see that the method of reduction order is quite useful, right? Because even though we just find one solution, okay, but we can proceed further to find the second solution by the method of reduction order. Any questions? Okay, that's good. Number 1 and number 2 are complex conjugates. Alright, so we let omega to be b minus a squared divided by 4. Okay. Then we can express lambda to be minus 1/2 of a plus I omega. And the number 2 is minus 1/2 of a minus I omega. Okay. Alright, so number 1 and number 2 are complex conjugates. Okay, so our normal solution y1 cubed, it's the exponential times ei dx. Okay. Maybe I'm too quick, so just say this is the number 1, right? Number 1 x. Okay. And this is equal to it's a complex function. The value is complex value. But we are talking about real solutions. Right? So that's why I say they are polynomial solutions, just nominal. You know the meaning of nominal? Nominal. Okay. But I translate. I try to translate. Okay. So do you understand the meaning of Chinese? You know that? Do I need to explain what is this term means? I think you know that, right? Okay, so it's called the nominal solutions because it's complex and but okay. But it will give you solutions, okay? So what is the solution? Well, you know it is called let me write down the formula, which is called the Euler formula. In high school, right? I think you learned the Euler formula from high school. No? Okay. Really? Did you learn complex number in high school? Yes, right? How come you don't know the Euler formula? No? Oh my God! Oh, it's a big trouble for me. Really? Wow. Wow, you don't know? Okay. Okay, I should assign a homework for you to read that. Because in the third part of this semester, we were talking about complex variables. And this is the very beginning for the complex. You have to know this, okay? You have to know that. Okay, so I will assign the first section, I mean maybe the first section in maybe chapter 13 of the textbook. Okay? So you better to learn this material as soon as possible. Okay, so now just believe me, this is the formula, it's correct, okay? It's correct. So this is just omega x just like the theta. Okay, so you can turn these exponential functions into the real part and the imaginary part. Okay. The other nominal solution is number 2x, right? So it's minus I dx. So this is E minus I omega x. So this is is cosine x minus I. The reason is that sine is an arc function. So sine minus omega x actually is equal to minus sine omega x. So sine is an arc function. You know arc function, even function, right? Okay, good. All right, so you see that. Now, okay, from the nominal solution, we can guess real solutions. Okay, these two functions, of course, are linearly independent. Okay, but we just say we guess that these two are two solutions of this order. Okay, so you have to check. Okay, you have to check, right? This is because that from our theory, the theory does not tell us directly these two functions are solutions of our original ODE, right? It just suggests these two nominal solutions only, right? Because the solution of the quadratic equation get to complex conjugate, so we have that. All right, but we think this is the true solution. Well, it's not hard. Let me check y1. Okay, let me check y1. Checking. And then you check the second one. Okay? Yeah. Oh, time's up. Okay, so you check by yourself. Okay, so let me say, please check by yourself. All right, at home. That y1 and y2x are solutions of the algebra. And that would be a happy ending. All right. Okay, so I will see you tomorrow.